So we're kind of in the middle, beginning middle of our quadratics unit for Algebra 2, and we're going to go back to an old topic on factoring. And we're going to use this technique of factoring, and we're going to be able to solve certain quadratics through factoring. And as much as some of you didn't like factoring when we first learned it, it's actually going to turn out to be one of your favorite methods of solving a quadratic. So first let's warm up with some old topics. Remember, the first thing we look for when we're factoring any polynomial is, are there any common terms that can be taken out of the problem? So this is an algebraic expression. There's a common 5 that we're going to remove from the entire problem. If I factor out that 5, think about what's left. I still have an x squared and then a minus 4. But what I just wrote down in red is further factorable. That's the difference of two squares pattern. So we're going to factor them into their, twin factors. So the twin factor for x squared is x and x. The twin factors for 4 are 2 and 2. And then if you make one a plus and one a minus, that's why there's no middle term in that pattern. So here I have 6p squared plus 15p plus 9. There's a common 3 that we should take out of that problem. When I remove that common 3, I still have a 2p squared plus, not that, plus 5p. Late, I'm already forgetting things. Plus 3. And then, just like on the last question, we want to look to see if there's any further factorization. Now, that's like your basic trinomial factoring question. So first terms multiplying together to give me a 2p squared would be a 2p and a 1p. And then I know the factors for 3 are 3 and 1. I don't want to put a 3 here, though, because that's going to give me 6. That's going to go too big. So what if I put a 3 here and a 1 here? That'll give me a 2p plus 3p, which is going to add up to 5p in the middle. So that last line I wrote down is our full factorization. Same idea here. We have a common factor of 2a that we're going to take out. Switch colors. So if I take out a 2a from both of these terms, now I have an a, and then a plus and a 4. And then this is just a linear binomial, so there's no further factorization there. Now this one, there's a common 4 I could take out. Taking out a common 4 leaves me with x squared plus 1x minus 1. And then I think about if I could factor, multiplies to -1 is positive 1, -1, and it's not going to add up to 1 ever. So that's actually the complete factorization of that expression, like the most boring kind of thing. So let's think about a different sort of a theory question. If I have two numbers where I'm multiplying them together, and I know when I multiply them together that the product comes out to 0, the only way that would happen is if one of these numbers is 0. Now, they both could also be 0, but either A has to be 0 or B has to be 0, or both A and B are 0. So that's one of the reasons why we spend so much time on factoring, is because once you can write a polynomial in terms of its linear factors, I know one of those factors has to be 0 when I'm going to solve it, meaning set it equal to 0. So we always said, like, that polynomial form of a quadratic, the standard form isn't really good for much. And that's true. That's why we spend so much time on factoring. So like here, I don't know what of this makes it equal to 0. So I'm going to rewrite them as a pair of factors. And then I'm going to know that one of the factors is 0. So through the art of factorization, it multiplies to give me -18. So, 9, 2, 6, 3, 18, 1. If you need to go back to just our regular factoring lesson, that's called 4.4 in the playlist. But I'm feeling 6 and 3 because if I use a positive 6 and a -3, remember how we used to check our arches here? It's -3x, and this is positive 6x. And if I add those together, I do get 3x, which is what I want in the middle. Now here's where it's going to get a little different from the previous lesson. Because this is an equation where it says find the solutions for when it equals 0, that means that either this number is 0, or this number is 0, or both could be 0. So if I do a little solving here and I subtract the 6, I get x could equal -6, or x could equal 3, and they are both correct. So this is where we use our manipulative skill of factoring, and then set our factors equal to 0, and they give us our two solutions. So here there's no common factor, and I notice that there's two terms, so it must be one of those special patterns. This is the difference of two perfect squares. So I'm going to rewrite this in terms of its twin factors. So twin factor for 4x squared is 2x and 2x. Twin factors for 25 are 5 and 5. And then remember the way the pattern works is one's a plus and one's a minus. So we're not done though, because we are trying to find the solution. I take each one of these factors and I solve them. So either 2x plus 5 equals 0, or 2x minus 5 could equal 0. And then we solve. So subtracting 5 from both sides. So essentially we took what was a quadratic term, or set of terms, and we broke them up into linear factors, which we could solve pretty easily through a couple of steps. Let's leave our answers as fractions. Negative 5 halves looks good to me. And you're going to get a very similar answer here when you add the 5 and divide by 2. The only difference is you get the negative and positive versions of the answers, which makes sense because of the way the pattern works. Okay. Next one here, there's no common factor. I thought there was at first, but that 9 does not have a common factor of 4. So this must be just a straight up factorization question. However, I do notice that the first and the last terms are perfect squares. So I'm kind of leaning towards the twin perfect square factors of both of those. So let's see if that works out. Now this time, because I do want to keep a middle term, it either has to be plus plus or minus minus, like the same sign. And if I look in the question, I notice the middle has to add up to a positive 12. So, oh, that didn't work. I think this is a typo. This is silly of me. 3, 12. This is a super duper typo. Well, let me do a little mental math real quick. 144 minus 4 times 4. 36. Yeah, this is a typo. Guys, goofy me. I meant to make this a 24. I think. Or no, I didn't. No, I did not. Oh, I wish I knew how to edit this whole video. This is so dumb. You know what this is? This is a sign that Abruzzo should just stop. So, I kind of screwed that up. Wasn't the twin factor of this a 2x? I think I wrote down 4x. That's why I was getting so confused. Oh my goodness. And then a 3 and a 3. And then when these are both positive, I get 6 and 6, which is 12. Yes. Sorry about that. Okay, so, but here's the good news. See how these are the same factors? So when I go to find my solution, what ends up happening is I get the same solution twice. So when I subtract this 3 over, I need to learn how to edit, because now this video is going to have that really dumb moment in there. You're all going to think little of me. All right, so the answer is negative 3 halves. It turns out it shows up twice algebraically. We're going to learn later on that that means that the solution has multiplicity, and we're going to eventually learn what that means for the actual graph of the function. But for now, just know that you get the same answer twice once in a while. All right, so I don't know if you noticed this, but all the questions we solved so far were in standard form instead of equals 0. In order for us to solve through factoring, they have to be in the blah, blah, blah equals 0 form. So first thing I'm going to do is I'm going to subtract this 24x over. And then I do notice there is a common factor here. So I can divide both of these or factor out an 8x that is in common. And when you factor out the 8x, so divide this and this by 8x, you still have x minus 3. Now, that 8x that you factored out, because there is still a variable term to it, that is its own factor. Like this is one factor that you're going to have to set equal to 0. And then this is another factor that you're going to have to set equal to 0 to solve. So this first one's really easy, just dividing by 8 and you get a constant x equals 0. And then over here when you add the 3, you get x equals 3. Lovely. All right. Ooh, yuck. We're 9. First thing I notice is this first term is negative. We haven't had a lot of experience with trying to factor when the first term of the trinomial is negative. It doesn't work out real well. It's not great. I mean, it's possible, but it's not ideal. So kind of notice they're all divisible by 2. What if we just divided everything here by not just 2, but what if we divided everything by negative 2? So the reason we're allowed to do that now, because we couldn't do that back in the factoring lesson, is because we are looking at an equation. So as long as you're dividing by a number, you're not unbalancing the equation in any way if you're dividing by a 4 or a 1/2 or a 2 or a -5 or whatever it is. So I'm going to go ahead and do that. So this becomes positive b squared. This will change to a negative b. This will change to a minus 30 equals 0. There we go. So that factors beautifully. B times b. And then my back numbers have to multiply to negative 30. 5, 6, 3, 10, 15, 2. But I want the arches to add up to negative 1. So what if we did a minus 6 and a positive 5? That would work, right? Because that's positive 5 plus negative 6 is negative 1. So now I'm going to take each of my factors. These guys are my factors, and I'm going to solve them. So usually this is about the time where kids start saying, well, can't I just take the opposites? Not actually what you're doing. I mean, these are really easy linear factors to solve that we've had these last few times. So essentially you can think of it as taking the opposite, but remember a few examples back here, like this guy, that was a two-step linear to solve. So it's not always as simple as just take the opposite number of your factor number. It can get kind of complicated. Here it's not in standard form yet, so I'm going to subtract this 13x, and I'm going to strategically place it in the middle because that's the order for standard form for a quadratic. Still can't believe I screwed up that factor question a while ago. The way. Alright. So here, this is one of those like you have a couple of choices because 6x could be 6x and 1x, could be 3x and 2x. And I'm kind of looking ahead in this problem and I'm thinking I want 6x and 1x, which is not usually what I want. But I noticed the middle number is kind of like relatively large and 2 is not large. So I need to create some bigger products. So I'm going to use the 6 and 1. And then for 2, multiplying to 2, I'm thinking, what if I put a 2 here? I knew it couldn't go in this factor because that would be a common factor of 2, and they don't have that. And they have to be the same signs to multiply to a negative 2. So what if I made them both negative? I think this works because this is a negative 12 and that's a negative 1, which will add up to a negative 13. So now take each of your factors, and this is one of those cases where you can't just simply take the opposite. You got to do a little work. You're going to solve. That one's not too bad. So like here, you're going to add the 1 and then divide by 6. Please leave your answer as 1/6 as a fraction. A rounded off decimal would not be accurate. And x equals 2 is the other solution. There you go. Alright, so this is probably stolen off of an old ACT test. The SAT test is a little more choosy about what they put on there as far as like algebra trick problems. But the number 11 I used to see a lot, very close at least, on your ACT test over the last 11 years that I've been looking at it. So the area of a rectangle is supposedly 36 square feet, and these are the dimensions that we have set up for this rectangle. It was derived from some sort of a story problem. And I know I find area of a rectangle by taking the length and multiplying it by the width. So the area of our rectangle, if I multiply the length and the width together, that would be x times x minus 9. And instead of like doing some math to find what the area is, I know the area is 36. We're going to kind of work through our algebra and figure out how big the dimensions of the rectangle are. Now, I know that if you do some guesses and checks, there's only so many numbers x could be, and you would eventually stumble upon it, but it's the art of the problem that we're looking for here, guys. It's not, can you answer this exact question, because it's not quite what we're going for. All right, so then it's going to say equals 36 on the right side. I'm just going to go ahead and subtract that 36 over. So it says equals 0, so we have standard form. The thing I wanted to show you in this question is we're going to get two answers, but we're going to have to cross one of them off, because multiplies to negative 36 adds to negative 9 would be negative 12 and positive 3. So when we solve these factors, you're going to get x equals positive 12 and x equals negative 3. But remember what x represented. It was the length of this rectangle. It's not going to make any sense to have a length of a rectangle that's negative 3 feet. But if I called this guy 12, 12 minus 9 is 3, and that would be the dimensions of our rectangle. So the dimensions are 12 feet by 3 feet. And you have to be careful on standardized testing because sometimes they'll say things like, what are the dimensions of the shorter piece of the rectangle, so I've seen them get crazy and say like, what's the perimeter of this rectangle, which isn't even the question, but you had to find all these things in order to calculate it. So in those cases, I don't care how you find the answer, as long as you got one and it worked. So if you did guess and check to the right answer, that's great. But what if the answer wasn't something really nice and guessable? And when we go on to our next level of math, that's usually the case, because guess what, guys? The real world is not pretty. They don't come up with nice integer answers all the time. All right, so this question, this is a very famous equation. It's when you drop an object on Earth, gravity is always affecting any object of any weight the same, and negative 16t squared plus s. The negative 16 is the effect of gravity, and measured in feet per second squared is the acceleration due to gravity. T represents time, and then the s represents the starting height. Because, if you drop something from 10 feet up versus 100 feet up, that's going to change the amount of time it takes for it to hit the ground, right? So if we start at 64 feet high, how long will it take until it hits the ground? So h over here is our final height, or ending height. Typically it's the ground. Not always, though. So for our final height for this problem, I want to hit the ground, so it's going to be 0. And then negative 16, I don't know the time yet, but I do know my starting height was 64. So if they want me to solve this through factoring, because that's what I'm trying to practice today, there's no way I want to factor this the way it looks right now, but what if I divided everything here by a negative 16? I chose negative. I don't want that lead term to be negative anymore. So 0 divided by anything is still 0, but this becomes t squared and then minus 4. Oh, that's beautiful. That factors into t plus 2 times t minus 2. So algebraically, I get these two answers. I get t equals negative 2 and t equals positive 2. But again, it doesn't make sense to say an object dropped for negative 2 seconds. So apparently it dropped for 2 seconds. And again, real world, not going to have a pretty answer like that. This is a very carefully created, intro problem for an algebra student. All right, so back here we have some practice problems. It's the same things we've been doing. None of this is any trickier than others. I'm assuming I signed this for you for homework. So I'm not going to do these on the lesson. But like I said, if you feel like the part that's really hanging you up on this lesson is just the factoring itself, then you need to go back to section 4.4 and just practice factoring algebraic expressions. If you're in the classroom every day with me, I can guarantee you that you are feeling okie dokie and ready to roll with factoring, because we are probably killing you with factoring questions over the last month and a half. So if you're trying to play catch up or kind of get some skills, you're brushing up on some skills, go back to that lesson. That would be my suggestion. We're moving on in quadratics. We're going to learn another method for solving quadratics next. So look forward to that.